Astronomy. Love it. It's the best. Far superior to astrology, as many of you know already. But we're going to talk about the HR diagram today. You guys have been working on a computer lab, Stellar Evolution HR diagram computer lab. Pretty boring computer lab. I apologize for that, but it was a good way to introduce you to some of these concepts. But first, we are getting into the life and death of stars. We're going to talk about how stars live, how they die, and it's, in my opinion, the most interesting part of astronomy. But before we do that, we got to talk about this thing called an HR diagram. And this HR diagram really helps astronomers to establish where a star is in its life cycle. Okay. So I'm going to get right to it. You guys, if you can, you don't have to necessarily copy this diagram down, but it's not a bad idea. I'm going to walk you through what the different aspects are of the HR diagram. So here is a perfect replica of the HR diagram, right? Okay. And a couple things I want to point out, right? First of all, H and R actually stand for two people that simultaneously developed this on really opposite sides of the world, Hertzsprung and Russell. HR. Doesn't matter if you know their names or anything really, but they both get credit for this diagram. So this is a chart that quite literally classifies stars by how bright they are and how hot they are. All right, but it's a little bit more than that. Once you plot the position of stars on an HR diagram, not the position, once you plot the stars on an HR diagram, you can immediately determine a lot of properties about that star. You can determine its mass, you can determine its temperature, obviously. You can also determine what phase of life it's in and how much longer it has to live. And you can tell how it's going to die. So let's get talking about the different aspects to it. So there are a couple things that are a little bit confusing on this. First off is there's actually two y-axes and there's actually two x-axes. So the first y-axis I have is absolute magnitude over here. And if you guys remember, absolute magnitude is the magnitude. Basically, how bright does a star appear if it were 32.6 light years away? Okay, so this is a more accurate way to recognize the brightness of a star. All right, so most people refer to this as like the true brightness of a star. Okay, now if you guys remember our talk about magnitude, I gave you the entire history of why the numbers are weird like they are. But if you remember, the brighter the object, the smaller the number. So up here I have a -10. Despite the fact that that's a small number, these objects are really bright. Okay, those are your bright stars. Down here, +15, these are your very dim stars. Okay, and then you see I have a +5 here and I have a 0 here. So 0 is not directly in the middle of the y-axis over here. All right, now the other y-axis over here, I'm not even going to write down. Okay, but what it actually is luminosity. And luminosity is a measurement of how much energy is actually coming out of the star per surface area, right? Per unit of surface area, right? And that goes up as you go up on the right there. It actually makes sense. It actually increases as you go up. All right. But luminosity is not a property that we talk about a lot in my astronomy class, so I'm just going to ignore it. We do have this new classification down here that some of you might have heard of if you've taken honors chem, AP chem, where you do a little spectroscopy, where you actually look through a spectroscope, or you look at the spectrum of different elements. All right, and that's what this is referring to. But the letters, again, are a little bit weird. You'll notice that it has this weird assortment of letters, O, B, A, F, G, K, M, right? Totally random and seemingly out of order. Well, similar to the magnitude story that I shared with you with astronomers originally classified stars strictly by looking at their color and assigning them a letter. Originally, the way they had it was more alphabetical. But then as we learned some things about stars, we learned that, hey, some of these stars that appear cold to us are actually really hot, and some stars that appear hot are actually really cold. So they had to rearrange some things. Short story is this. The brighter the star, the hotter the star, the more towards the left side of this HR diagram. It then decreases going from left to right. So it cools down. So that's actually our second x-axis. If we were to do the x-axis up here, it would be temperature in Kelvin. All right. And the temperature in Kelvin, this would be insanely hot over here, like 30, 40,000 Kelvin. Okay. And then over here would be closer to like 3,000 Kelvin, which is still pretty hot, right? But way cooler than 30,000. Okay. Now, these letters, right, they actually represent different temperatures on the surface, because here's an interesting thing. When a star changes its temperature, it actually changes the color that it portrays. Really, really, really hot stars, these 30,000, 40,000 Kelvin stars, they have an electric blue color, kind of like a lightning bolt. These are electric blue. All right. It should be a blue color I'm using there, but that's purple, you'll notice, because I only have one shade of blue. But this is your electric blue, lightning color. Believe it or not, lightning is blue. A lot of people think lightning is yellow, but it is not. Lightning bolt is roughly 30,000 Kelvin, right? So the temperature is actually the same, so that's why they have the same color. B-class stars. These are just your standard blue stars, okay? Now, in astronomy, blue is hot and red is not. All right, so as we go from left to right here, we're going to go from more energetic forms of visible light, higher energy, to lower. Way over here on the right, the M-class stars, these are red. Okay, red stars are the coolest. All right, not that they're, you know, awesome or anything, but they're literally the coldest stars in our universe. After the red class stars, you do get to the Ks. Ks have an orange color. And then the G-class stars is a yellow. Hey, I know of a yellow star. All right, the sun is a yellow star, and it is a G-class star. All right, F is also yellow again, but this is a pale yellow. All right, and I don't have a word for pale yellow other than this, pale yellow. Okay, I think I got my point across. And then the A-class stars are just white, which I will represent using lead. Okay, so here we have a really broad look at the different axes on the HR diagram. The sun is a yellow class star. It's the G class star. And it also has about a +5 absolute magnitude, which is why I have that +5 there. So what I'm going to do is I'm going to take my pencil, all right? I'm going to find the G. It's actually a little bit brighter than a plain old G. It's actually what we call a G2. So it's slightly to the left of the letter G. All right, there's my pencil pointing straight up. Then I'm going to take my other pencil here from +5, and I'm going to connect those two, all right? So basically right here is the sun, okay? It's a +5 G2 class star. This is the sun. And you'll notice it's pretty much smack dab in the middle of the HR diagram, and that's because the sun is smack dab in the middle of normal, all right? It is an average star. It is nothing special. It is average in size. It is average in temperature. It is average, okay? And it falls in this group, right? That actually, you know, I'm going to draw this weird concave kind of pickle shape here. This is the main portion of the HR diagram. It's the main portion because we call it the main sequence. Okay. Main sequence stars are stars that fuse hydrogen into helium. I can spell. I can spell H. Don't doubt me. Hydrogen fuses into helium. Okay. These are main sequence stars. Now, our sun, S-U-N, not S-O-N. That would be really weird. Our sun will fuse hydrogen for about 10 billion years in total. Okay. Right now, the sun has fused through about 50% of its hydrogen. So it's middle-aged, right? It's going through its midlife crisis. Just bought a convertible. It's going out with a much younger star. It is really embarrassing. But anyways, it has about half of its hydrogen left for another 5 billion years of hydrogen fusion. Okay. And actually, we're gonna stop here because this is a good place to stop. There are other portions of the HR diagram. What happens to stars when they die? How long do these stars live? How long do these stars live? And we're going to talk about that in the next video. HR diagram. Dramatic pause. I'm still dramatically pausing. I'm continuing with my dramatic pause. I don't know what's going on with my hair here, guys. My hair is getting out of control. I need a haircut.